All right, let's go ahead and let's get started, folks. I'm going to try to finish up with the discussion of gas pressure today, and then do the one calculation we have to do in this chapter. Hopefully, we can try to get through the discussion of a kinetic energy and temperature as well before we leave for the break. And then when we get back from break, we'll continue on with discussing liquids and solids. And then we'll move into our chapter in on gases. Okay. All right. So let's go ahead then, and I would like to start out with two problems from the chapter 13 problem set. Let's go ahead and let's take a look at number 4 here first. So let's do number 4. I'll ask you to do this, just balance the equation, write it on your paper, and then when we come back, unpause the video, and when we come back, I'll go over this with you. These review problems here are going to help us with the work that we'll do moving forward. So you always need to make sure that you can balance equations, folks. Identifying the type of reaction that's being described is important, but I think moving forward, it's not going to be as important, but let's practice this anyway. So with the first problem of the day today, I'd like you to do number 4 in your problem set. Let's balance out these two equations and then classify them. Okay, go ahead and get started with it. Okay, let's go ahead and let's take a look at these two equations here. Hopefully the first one you recognize them as being let's go ahead and work this one out here. This is a combination reaction, so let's go ahead and write that down first. So we have a combination reaction. Okay, combination reaction. Balancing this out here, you got to make sure that you balance out the atoms here. 2 bromines, put a 2 in front of the lithium bromide here. If you do that, you need 2 lithiums on the left-hand side. So that balances out our equation for us. Okay. We're going to take a look at the second one. And the second one is a combustion reaction. And we said then that with a combustion reaction, it is a type of combination or synthesis reaction because you're combining 2 reactants together. But in this case, then, one of the reactants is not an element, but a compound. But if the compound ends up being a hydrocarbon, we know then that the products that will always form will be carbon dioxide and water. So those are the key features of a combustion reaction, which is a specific type of combination reaction. Okay, with these combustion reactions, remember what you need to make sure you do: balance out the carbons first, then go ahead and balance out the hydrogens, then leave the oxygens for last, because if you have to use a fractional coefficient here, you can, but then you can just multiply that out. Okay, so hopefully you did that. If you did that correctly, then the balance equation would give you a 2, 7, 6, and 4. Okay. All right, very good. Hopefully you got that. If not, please make sure you write that down on your paper. Okay, and then you'll submit that towards at the end of this period. Okay. All right, let's go ahead then. Let's take a look at the next one. So that was number 4 in your problem set. Number 5 here is going to give us some practice on exactly what we just did in chapter 12, okay, and what you had learned already. So you need to keep this. You need to make sure you know how to do in chapter 14 when we do gas stoichiometry. You'll need to make sure you remember how to do the stoichiometry. This time we just deal with gases. Okay, and so let's go ahead and work on this particular problem here. Take about 2-3 minutes to work on this problem, and then when we get back, I'll go over it with you. Okay, so go ahead, work on this problem right here. All right, let's go ahead and let's work this problem out. Number 5 in your problem set, it's stoichiometry, and so make sure then you always start out with a balanced equation. Okay, so let's go ahead and let's get the balanced equation for this particular problem here. Okay. So we start out then with dichlorine heptaoxide, so Cl2O7. We're going to react that with water. Okay, to form then for us what is called perchloric acid, which is HClO4. Balancing out the equation to be 1, 1, 2. Okay, that'll balance out the equation for the equation for us. Okay, let's go ahead then. Let's write down what we were given. They tell us in this problem that we start out, or they're asking then, if we get 56 of the starting amount, that is the quantity that's given to us, is a quantity of the product. They're telling us that if we end up with this amount of product, okay, how much of this reactant did we start out with? So the given amount here is the amount of what we're given to start out with is the amount of perchloric acid. What they're asking us to solve for then is the amount of dichlorine heptaoxide. Okay, so this is basically what we did when we figured we were calculating the theoretical yield, but with the theoretical yield, remember, we were given the amount of the reactant and we had to find the product. Here, they're just changing things up a little bit here, where they're saying that if you have this amount of product, how much reactant did you start out with? But it's still the conversion. Remember, with conversions, you just answer 3 basic questions. And the first question is, what is the given amount, the given quantity? The second question is, what do they want you to solve for? What is the quantity that they want you to solve for? And then the third one is, what are the conversion factors that you'll need? And we'll figure that out as we work out this problem. Okay, so we've answered the first 2 questions. Let's go ahead and answer the third one. So let's go ahead and set it up. We're starting out, whoops, sorry, let me go ahead and do this. So we're starting out with then, okay, so the starting quantity here then is going to be 56.2 grams of HClO4 perchloric acid. What we're solving for then is the grams of Cl2O7. Okay. All right, so the first conversion factor then is going to be the molar mass of perchloric acid. 1 hydrogen, 1 chlorine, 4 oxygens then will give you a molar mass of 100. So 100, so it's going to be HClO4 over 100 grams, and we're dividing here so we can cancel out the unit grams of HClO4. Okay. Second conversion factor, remember, is going to be the mole ratio perchloric acid to dichlorine heptooxide. Okay, so it's going to be 1 mole of Cl2O7 over 2 moles of HClO4. And then the last conversion factor then is going to be the molar mass of dichlorine heptooxide. And we're going to multiply by that. 2 chlorines, I'm sorry, this is Cl2O7. 2 chlorines and 7 oxygens is going to give you a molar mass of 182. So 182 grams of Cl2O7 over 1 mole. Cl2O7. All right, so with that said, if you set it up this way, all the units will cancel out and you will end up with grams of Cl2O7 on both sides of the arrow. Just go ahead then and you punch the numbers into your calculator and you end up with an answer that is 51.1 to 3 significant figures, 51.1 grams. Okay. All right, so make sure you review that, folks. Make sure you review that. If you don't remember how to do this, make sure you come by. I will still, I'll have my office hours today as well before we leave for the break, okay? So come on by and ask your questions if you have any on this, okay? All right, let's continue on then. Okay. And let's talk about gases, okay? So we started this unit by talking about gases. We know what the properties of gases are, both on the macroscopic level and how we can explain those properties on the macroscopic level at the microscopic level. So we know then that gases have no volume of their own. They have no shape of their own. They take the shape and volume of their container. Gases tend to be colorless, most of them. They're odorless. And so how do we know that gases are there? How do we know then what's the one property of gases that we can measure that tells us that it's there? Now, some gases have color, and obviously other gases, they interact with us and sometimes in very bad ways, and sometimes, and oxygen obviously we need. And so we do know that the gases, they're based upon our experience with it. But one property that all gases have that allows us to know that they're there is that they exert this pressure. And the kinetic molecular theory, remember, tells us then that gas particles in any particle are always moving, and that the way the gas particles move is that they flow, and so they move in such a manner that they interact with their environment. They interact with each other, and they interact with their environment, which liquid particles do as well, which we'll talk about once we get back from break. And solid particles, not so much. Okay, so solid particles, we'll talk about that also after you get back from break. Solid particles, they do interact with one another. They do move, but they move in a different way than liquid particles and gas particles. Okay? So gas particles, according to kinetic molecular theory, they move, they interact with one another. That interaction, and that's what we're going to focus in here, that interaction is one in which they will collide with one another. And you can imagine this, if you have a bunch of balls moving around and they're hitting each other, they're hitting the walls of the container. That interaction is what we refer to as an elastic collision. These gas particles that collide with one another, and this the way that we describe elastic collisions is that when they collide with one another, they don't lose any of that kinetic energy. And so remember, I defined for you yesterday kinetic energy as being the energy that's associated with moving objects. Okay, so kinetic energy can be calculated for. We can define the kinetic energy as the energy for any object that has a mass, okay, and everything has mass and it's moving. Okay, so I gave you the equation yesterday. I introduced that to you, and I showed you how you can use that equation to calculate for it. But any moving object has a certain amount of energy, and we'll get to that hopefully today towards the end of this year. But as these particles move and they collide, it's that collision that creates what we call gas pressure. And that's how we know that gases are there. Gases always exert a pressure. Okay? And the reason why we can feel that pressure is that we can immerse ourselves in that particular gas. Just in the same way that we can immerse ourselves in a liquid, and I think everyone's experienced this before. Okay? And we know that it's exerting pressure because, for example, when you go into a pool and you dive down towards the bottom, or if you're out at the ocean and you dive down deeper and deeper, you can feel the pressure that the liquid, the water, is exerting on you fairly significantly. Okay? Same thing with gases, and we'll talk about gases in just a moment. We've also experienced changes in gas pressure as well. If you've ever gone up to the mountains, okay, you've experienced this change in pressure. And so we'll talk about that towards the end of the period today, and that's my hope. But we know that gases are there because they can exert this pressure, and we can measure that gas pressure. And so, like I said, with volume, it's somewhat difficult for us to measure the volume of a gas. Now, obviously, we can measure the volume of the gas based upon the container it holds, but that doesn't tell us much more about the gas itself. But from the pressure of the gas, we can calculate then for the volume of volume. We can calculate then for the number of particles that the pressure that particular gas sample has. If we can measure the pressure of a gas, we can obtain other characteristics of the gas as well, and that's the basis of the gas laws that we'll learn about in chapter 14. So we can measure the pressure. If we can measure the pressure, if we know what the pressure of the gas is, we can identify how many particles there are in the gas, the temperature at which that gas is at, and also the volume that is occupied by that particular gas at that particular pressure. So that's why we need to talk about gas pressure at this moment. Okay. All right. So what then keeps this balloon inflated? Okay, the balloon here, obviously we know then occupies a certain volume, obviously, but that volume changes. Why does that volume change? Well, as we add more gas particles into it, the volume changes because the pressure inside the gas, inside that bubble, inside that balloon is pushing out on the balloon, thus increasing its volume. Okay? So as you increase the pressure there, you'll see that the volume of the balloon expands to make sure then that it can equalize the pressure outside the balloon and inside the balloon. Okay? So the pressure exerted by the gases, as you put in more and more gas particles, it increases in there. Okay? Okay, so that's what we're going to talk about. Okay, so gas pressure is the result of force, and I'll define what a force is in just a moment, exerted by the gas per unit area of an object. Okay, so this is an equation I can show you in just a moment. But the force is a quality of an object that it exerts on. It's a property of an object that it exerts on everything around it if it is in motion. Okay, and so we'll talk about what that force is in just a moment. But do understand this? What this is basically telling us is, as these particles are moving around, they are bumping into everything. They are pushing on everything around them. And so because of that, they exert what we call this gas pressure. Okay? And so gas particles have mass, okay? And because they have mass, okay, and because they're moving, they will exert this force. Okay? They exert this force, and we can use Newton's second law here to calculate them for this amount of force that the gases exert on this balloon and also on everything else around it, okay, and on each other. Okay? So let's go ahead then and let's talk about what this force is. What is this concept of force here? What is this idea behind force? And how is it related to the mass and the acceleration of an object? So we'll define both terms for you in just, I'll define both terms for you in just a moment, okay? All right, so that's how we know that a gas is in there. So we can't see the air that we blow. This is the carbon dioxide or helium or whatever gas we put in here, we can't see that gas, but we know it is there because of the pressure it exerts on this balloon and thus expanding that balloon. Okay. All right, so let's go ahead then and let's talk about force really quickly. Okay. So like I said, force is a property that every object in the universe has as long as it's moving. Okay, as long as it's moving. So that force and that force then is a way that an object interacts with everything around it. Okay, so in physics we define force very simply then as a push, okay, or a pull that an object experiences. Where does that push or that pull comes from? It comes from other objects. So you can imagine this here. For this blue ball right here, for this blue ball here, I can come in and I can push on this blue ball. So I move my hand. So the movement of my hand or the movement of my foot pushing on this ball here is a force. So forces are simply a push or a pull that one object has on another. Okay, and this object here will not change the way it moves unless it is pushed or pulled by something else. So once this ball gets pushed, it can go on and it can interact and it can push on another object, on another ball. So you can imagine if you're playing pool here, we push this particular blue ball here, if this is our cue ball, it can go in, it can collide with another ball and push on that particular object. Okay? So my push or my pull, so this object then, this ball then has a certain mass. Okay, so let's go ahead and do this. Okay. This ball then has a certain mass. So we'll write this in as M, has a certain mass. Okay. And I have a certain mass. So I go in and I push it. And when I do, this ball changes the way it moves. Okay, so that's what you got to make sure you keep in mind. Okay. So with that said then, a force is defined then as a push or a pull that one object has on another. So forces are pushes or pulls that one object has on another object. Okay. Okay. So with that said then, let's go ahead and let's continue on. Let me erase this here real quickly. Okay. All right. So from Newton's second law, which I showed you already, okay, this force can cause another object to change the way it moves. Okay, so based on Newton's second law, let me just write that for you down again real quickly. The force that an object feels, or an object feels, is going to be it's going to change the way it moves depending on the mass of the object and this here. Okay, acceleration is basically speeding up or slowing down. As an object speeds up or an object slows down, it is accelerating. It's changing its speed, or changing its direction. Okay, so in physics, then we learn then that if a force is applied to an object, if a force is applied to an object, it can cause the object to change the way it moves. Okay, so this is our force here, and so the relationship between these two and force we explain much more in physics, but for our purposes then, as a gas particle moves, it has a certain mass, it will change its direction. Remember, it won't change its speed, it won't change its speed. That speed is dependent on the temperature. It won't change its speed, but it will change its direction. Because, again, it won't change its speed because we know then the kinetic energy stays constant for a particular gas particle. So it doesn't change its speed, but it will change its direction. So a gas particle, as it moves in, it collides with an object, it changes its direction, but as it does so, it applies a force. It applies a force on whatever object it collides with. Okay? All right, so with that said then, that's Newton's second law. And as it pushes in, as it collides, as the gas particle collides and then changes the way it moves, and thus it exerts a pressure, it exerts a force, it exerts a pushing force on other objects around it. At that point then, it also exerts what we call a pressure. Okay? So what is this pressure? Well, let's imagine this here. Okay? So if I come in and I step on your foot, okay? I step on your foot, okay? I'm exerting a force on it. Okay, I'm moving my foot and I am pushing down onto your foot. Okay, and so I exert a force on it. That force on your foot, then it's going to apply it over a certain area. Okay, that's what we call pressure. Okay, so the pressure then is force applied over a certain area. So if I apply my force, if I push my foot down on your foot, I'm exerting a pressure on it because I have a force and I'm pushing down on your foot and then over a certain area, and that's going to be pressure. Okay, so with that said, then you can imagine if an elephant steps on your foot. Okay, that elephant then will exert a greater pressure. Why? Because he is exerting a greater force on your foot. Okay, And so with that said, then you can also see then, so there is a relationship between the force, okay, so the force of my foot, okay, the force of this foot here, and I'll call this one, is less than the force of the elephant here, okay? So he exerts a greater pressure because he has greater force. He's pushing down more on your foot than I'm pushing down on your foot, okay? So what do? What if I put on a pair of high heels? And you can imagine then if I put on a pair of high heels, okay, okay, then and I'll finish up with this. And you can imagine then that if I put on a pair of high heels, the forces are the same. Okay, so the force, so I'm not exerting greater force. The forces are the same here. Okay, so I'm still pushing down with the same force, but what is different? The area. The area over which I push is going to be smaller, okay, when I put on a pair of high heels than when I'm wearing my shoe. And so the pressure exerted by an object depends on two factors: the force in which that's being applied, and also the area over which that force is applied. And so pressure then is defined as the force per unit area. Okay, so I'll finish up with this here. We'll pick up with this discussion on when we come back from break. Okay, so with that said, then the greater the force, the greater the pressure is going to be. So if you notice from this equation here, these two are directly related, whereas the pressure is inversely related to area. That means that as the area gets smaller and smaller, the pressure also increases. Okay, so the pressure then is defined then in terms of both the force and the area that's exerted by an object on another object. And so you can imagine that with gases then, gases are in constant motion. Gases are in constant motion, okay? And when they collide, they're going to collide over a certain area. Now, all gases have a certain volume as well. And so when they make contact with either another gas particle or with with the surroundings, the container, it will collide, it will interact with a certain area. And so that means then, remember, since gas particles are very small, this would be very small, the pressure they exert will be somewhat larger, but because they are very small, the force that they exert are going to be somewhat smaller as well, even though they're moving at a large speed. Okay? And so what we're going to do then is, when we get back from break, we're going to pick up with this. Now, I will not ask you to calculate for force or calculate for pressure here, but I do want you to see then the relationship between force and pressure, what it means in terms of gas motion and in terms of the pressure the gases exert. Because if you have kind of a basic understanding of that, it's going to help you understand then the relationship between pressure and volume and temperature. And so we'll continue talking about gas pressure when we get back from break. I hope you folks have a good break. Try to get some rest and try to just unwind a little bit the best you can under the given circumstances. And I will see you folks back then. I guess we'll find out. I'll see you folks back hopefully either at school or online here when you get back from break. Okay. All right. So have a good break, folks, and then I will see you once we get back from break. Okay.